So I think I'm gonna watch these videos for a while. I've watched all of these ones for off stream. While I've watched all of these ones, and then I'm gonna work on the thing. I think I'm gonna read the C's module. I did some things, try to play around with the thing, but this script here that creates visualization, but I didn't get anywhere. It's still hard for me to understand what Vivex did on this final file here. So I tried to put some print statements there, but nothing was showing up. So yeah. So let me start counting. I'm gonna open the curtain there a little bit. I think I'm gonna read this stuff. Maybe do some coding stuff as well. Some of these games here that I found online. This one I found online, and this one Vivex told me about it. But this seems to be more advanced, so I'm curious to see. I think it's like as more challenges that you can do to train. Each language will start with Python. This one also looks good. Also got a light from Christmas from my dad. So that's really good. Which means it's
over, so
it's gonna be better to record at night when I want to.
100 and 0. So we can see a pattern here, right? The x-coordinate in screen space is just going to be the x-coordinate in grid space times the width of a brick. So this is 0 times 50 is 0. This one is 1 times 50 is 50. This is 2 times 50 is 100. This one is...
Yeah, this chili tomato. I really enjoyed these videos. They're really good and instructive. I obviously didn't do anything yet of the project. I'm just watching to get used to the way that things are built. Later on, then I'll try to build my own stuff after I'm done with the things in Python.
Is going to be, what is it? 150 and 0 in screen space, and so on and so forth. So we can say that the screen x of the top left-hand corner of a brick is equal to its grid coordinate in the x times the width of a brick. And it's the same for the y, right? In the y part of the thing, you just multiply the y grid coordinates times the height of a brick, and you get its y coordinate in screen space. So screen y is equal to grid y times brick height. And if you look at just pick a random brick in this grid here, the brick 2, 3, its screen coordinates of its top left-hand corner is going to be 2 times the width, 3 times the height, 175. Quite simple. Now here we have assumed that our entire grid starts at 0, 0. But in general, it's not going to start at 0, 0. So to find the coordinates when the grid does not start at 0, 0, you just got to take the start coordinate of the grid, which is this vector here, and add that to this result here. So if the grid starts at, let's say, 25 and 100, then you would just add that vector to these result vectors to get the actual top left coordinate in screen space. So here's the final expression to get the top left-hand corner of any brick in screen space. You take the position of the top left-hand corner of the grid, and you add to that a vector that's just x times the width of a brick and y times the height of a brick. So we create a rectf here, and we got to pass it now a vector for its top left-hand corner. So we go top left, and that's top left-hand corner of the grid, plus vec2 x times brick width and y times brick height. And this, some of these vectors here will give us the coordinate of the top left-hand corner of the brick that we're creating. Now we need to pass in the actual dimensions of the brick, which is just brick width and brick height. And there we go. We finished creating our rectangle. Now we got to pass in the color, which was selected up here from the array. And then we finish the brick constructor like this. Notice that we're not using an init function like we did with poo. We're just creating a temporary brick, and then we're assigning that to the element in the bricks array. Honestly, I'm not sure why I didn't go with this approach in the poo game, but whatever. Now this concept of using nested for loops and grid coordinates with x and y, it's a very important concept. So if you don't understand this after the second watch through here, you should try stepping through this code. And actually, I'm going to create a tag in the commit history called T20 grid. And what you can do is you can create a branch off that tag so you can get to this code, and you can set a breakpoint here and step through the code and try to analyze it yourself. And even if you do that and it still doesn't make any sense, you can ask questions on the Discord or the forum. By the way, there's a little more sophisticated way of calculating this index in the brick array that doesn't require us to use a separate index and update it, but I will cover that later. All right, now we got a couple of errors here, and they have to do with the fact that brick is no longer a thing. Now we have an array of bricks. So what we're going to do is we're going to, instead of calling brick.draw, we're going to loop through all of the bricks and call draw on each of them. Now normally you'd use a for loop, and you go, for int I is equal to 0 as long as I is less than number of bricks, I++. But we're going to do something different. We're going to do for, and now we're going to do constant brick reference b. Then we're going to do colon bricks and do our curly braces. And then, no, that's not a fucking curly brace. There we go. And then here, we'll call b.draw. So what is this dark magic? The compiler seems to like it, but maybe you don't. It's actually pretty cool. It's called a range-based for loop, and it creates a loop that automatically goes through every element in the array. So for every element, it gets a reference to that element, and then inside the body here, you can do stuff with that reference. So what I'm saying here is for each brick b in bricks, call b.draw, and that b is a constant reference. And that's all it is, and it's super simple, and it works fucking sweet. So we're going to use it whenever we can. New thing for today. Now here we want to do basically the same thing. So we do our range-based for loop, like this, and then we call b.doCollision. And it's not going to like it, and the reason why is because object has type qualifiers that are not compatible. Basically, we are getting a constant reference, but do_collision is going to change the brick. So we can't have a constant reference, we need just a normal reference. And now the brick can be changed because we have a normal reference, everything's fine. So now for every brick, we do collision with ball. Now, if we get a single collision, we don't want to keep checking all the other bricks. So what we're going to do is we're going to limit ourselves to one collision per frame. That makes more sense. So what we can do is we can go break. So for every brick, we test for a collision. If we find a collision, we play the sound effect, and then we break out of this loop. So we end prematurely before checking the rest of the bricks. That's what this break does. I'm not sure if I've introduced it before, but I don't use it very often, but it's a thing. I use it sometimes. So we break out if we have a collision. And this should work. Let's build it. And let's see what we got here. All right, we've got our motherfucking array of bricks here, and it looks like it's working fairly good. There we go. We collide off our thing there. Sweet. And let's fucking try a little bit more out here. Okay, good. Yeah. We're doing it, baby. We are rebounding off of the bullshit. I want to get one weird one in, but I guess I can wait for later. Wait, check this. Yeah. So we got some problems, obviously. But anyways. So, first things first, I don't like it that all of the bricks are like connected like this, drawn. I want a little bit of separation between church and state here. So what I'm going to do, two things. First of all, we got to celebrate good times. Come on. What do we do here? Oh yeah, made a grid of bricks. It was sweet. There we go. I updated brick as well. What did I do in here? Oh, I added a default constructor to brick. Yeah, I'll put it on the same. You can tell I'm getting lazy now. I'm just putting everything in the same commit. But anyways, so now what I want to do is be able to draw some borders basically between the bricks. But I want the bricks to still logically touch each other. I just don't want them to look like they're exactly touching on the screen. So what I'm going to do is, first thing first, I'm going to go into rectf. I'm going to create a function, and this function is going to be called so it's going to be called rectf. It's going to return a rectf. It's going to be called get expanded. It's going to take a float offset, and it's constant, so it doesn't modify the object itself. So what is this going to do? Well, let's say you got a white rectangle like this, and you call get expanded with a parameter of 2. It is going to return a rectangle which has been expanded by 2 units in each of the directions like this. So, and if you call get expanded with a negative number, it's going to return a rectangle like this. So what we want to do now is, well, first of all, I'm going to implement this function. And it's very simple like this. You just add and subtract the offset from all the sides. And now in brick, we're going to add a little constant in here. Static constant expression float padding. So here's the padding that we'll have between bricks. And in draw, instead of drawing the rectangle, we're going to draw the rectangle dot get expanded negative padding. And that should give us a little bit of breathing room between our bricks, or cause us to fucking shit the bed. Let me just think here for a second. All right, it should be left minus offset, because we're going to a positive number would offset it this way. So it should be minus, and these guys here also all need to be changed. Like so, and if we build that, good and good. Now our bricks have spaces in between them, which is aesthetically more pleasing for me. So we'll commit our brick padding bullshit here, and now what I want to do is I want to set it up so that the grid is maybe a little further down and maybe covers a little more of the screen. So what I'm going to do is just tweak some of those constants there in game.h. So I'll make the number of bricks across 18, and let's change the top left corner to go down a little bit. Something like this, and now we can run this, and we can do a little bit of testing here. Okay, well that was really bad. Let's see what else we got. What else you got for me, game? Looking so far not too bad. Keep going. Okay, that is very bad. And here's where I'm going to cut off part 2. We've got all the basics implemented, but as you can see, things are still a little wonky. Now, if this is your first time through, go back and rewatch parts 1 and 2 in detail like I explained at the beginning of part 1. If it's your second time, then it's time to code it up yourself. I mean, you can rewatch a third time or more if you think you're not ready, but I recommend at least 2 watches. So to code it up yourself, you're going to create a branch at the start tag, and you're going to go nuts, preferably with as little peeking as possible. Now, after you get the code working at least as well as at the end of part 2, you've got 2 choices. If you want a hard challenge, you can play the game yourself and see where it fails in its physics. You can test it out, try to analyze what's going on using the debugger, and manipulating the code yourself to reproduce errors errors, and then you can come up with a fix. You can add some logic to better handle those cases where it's failing in its physics. That's option 1. Option 2 is you can just proceed straight directly to part 3 and see how Chili improves the physics. Now, if you do try and attempt it yourself, don't bang your head against the wall bloody. Just give it a shot if you're interested, and if you get stuck or you're just at a loss on what you should do, move on to part 3, and Chili will drop some knowledge bombs on you. Either way, if you like the video, please click the like button. Helps a lot, and I will see you soon in part 3 of Fartanoid.
I think what I needed, or what I really need to understand is the sys module itself. Because when I was trying to play around with the script, I didn't understand the workflow of this thing. So I raised a bunch of stuff as well. Yeah, I just don't understand the sys.modules. What's gonna be passed into this class. The other script had this thing here. So import lib, import module. This module provides access to some variables used or maintained by the interpreter and two functions that interact strongly with the interpreter. It is always available. App flags on POSIX system where Python was built with the standard configure script. This contains the ABI flags as specified by PEP 3000 something. Audit hook. Append the callable hook to the list of active auditing hooks for the current sub-interpreter. When an auditing event is raised through the sys.audit function, each hook will be called in the order was added with the event name and the type of arguments. Native hooks added by PySys or add audit hook are called first. This Python implementation detail when tracing is enabled is set trace. Python hooks are only traced if the callable has a can trace member that is set to a true value. Otherwise, trace functions will skip the hook. So I need to understand what a hook is in Python. That should be something that keeps track of things somehow, but I really don't understand it.
We are going to continue to look at some of the internals in Flask. This time we're going to look at request hooks. Many times when you have a larger application, there are some actions that you need to perform for many requests. So for example, in an application that supports authentication, you will be authenticating the user every time there is a request. So these actions that need to be performed for all requests will be repetitive if you copy them into every route. So for that, we use request hooks. We're going to look at a new example now to show how those work. In example 4b, we have an extension to our +1 application that we've seen before. So let's open that up. So here we're importing another context variable from Flask. That's called g. You can see here in line 7, I have a new decorator. It's called app.beforeRequest. The function that's associated with that decorator will run before Flask dispatches the request to our route function, regardless of what that is. In this, I get that in one place, and it runs for both routes. This application. The g context variable
I don't think those hooks are related necessarily.
Hey everyone, in this video we're going to be talking about the sys module and how to do various things like change where modules are searched for and a couple other things. So this is kind of like a miscellaneous video, a bunch of cool tips, and I want you to better understand how modules work in Python. So the very first thing I want to show you was this document here from the documentation documentation, it's talking about the standard modules, so the modules we've been using. Well, so far, most of the ones we've used have probably been available to you. However, some of them might not be. So for example, this winreg or winreg, this module is only provided on Windows. If you're on Mac, you can try to import that and you'll get an error the time. However, there is a module that should be available all of the time, and that is sys. And sys is used if you want to interact closely with the interpreter.
I hate when pages do stuff like this. Biggest issue with the documentation is that they show you the things, but they don't show you how to use them. So hopefully probably someone on Stack Overflow has done something with this stuff. What I want you to do is get all code objects from scripts. So I wanna let me open the thing here. Here I have an example from Kaggle of one of the exercises. Ideally, I want to build something that can take this script and open up and get all the code objects from all these files, from all the libraries, everything that is being used here, and then create a graph that connects all of them, which is slightly different than the one that Vivex did, because that one imports the libraries and not necessarily the code objects and their relationship. And also I would need to get the file that those things are as well, somehow, so I can put them together in the graph. So let's think. How can I search for this? Maybe I just do it quite literally. Maybe I can check for type and get the source. Maybe that's the stuff. I think I will erase everything here and start from scratch, just so I can have things more clear in my mind. So I want you to import AI tester. It's with caps lock here. And I want you to loop through this file here. Question is, will I have... I remember this was the login thing I was studying. So I think I'll have to put this on a function, on a main function, so it's easier to call on the other file. So I don't have to use the operational system, the OS library. Usually they say you can do import OS. You can just do os.sys system, then the file, and this will run the file through the operational through the operational system. But I don't think that's exactly what I want. So I'm just gonna create the main function here. This script here creates it gets a data set for the house prices, which is another project that I had. I got a project from Kaggle and they used a different data set just to test this thing out. So it gets the data sets, then drops the null values, creates the train test split, then gets the columns with less than 10 unique values for categorical data types. Then gets the numerical. Here I don't remember exactly on how to encode data, to shorten the code, you use Spanish. So it's creating the one hot encoding, transforming the categorical values into numerical ones. Then joins the data set again and is using XGB regressor to train the model. Then it tests the different one hot encoding to compare the accuracy. And it does it again here. Yes, that's pretty much it. It's not that important. It's just so I can test this thing here. Oh, I forgot to put this so it runs only when I call it from this file. So ideally what I want is something where I'm just gonna call I want to loop through this file, loop over the file, then let's see, categorize code objects from file. God damn, dude. Then I have to see, got source code for each of the objects, categorize the... Yeah, that's the problem. I'm gonna have to do a recursive function, I think, which is gonna grow a lot. Because each object, I'm gonna get the source code and then I'm gonna loop through the source code of that object and get the objects of that file. And do that until there's no more objects. So I can maybe do that recursively and create lists where I put each object in a specific link. But the problem with that is that I'm not gonna be able to have the connection from which one, because I'm gonna have... The only way I can think about doing this is separating them by function or variables and that kind of stuff. There isn't a clear way to separate them by a more intuitive way. No, but I think it still might work because I'm gonna get the source code for this. Yeah, categorize the objects from the file, then get the source code for each one. But that's the thing. Once I have the source code, how do I connect everything together? Maybe I can just try and see what happens. Categorize the files from source code. And do that recursively until there is no more files. Yeah, I think that's the path. So I need to figure out how to look through Python file. The thing is, I don't want to run the script. I just want to look through it. That's the problem. So how can I search for this? Because if I search for debug, it's gonna show me PyCharm stuff, not what I want. And if I call the function, it's just gonna run the script, but I'm not gonna. So basically, what I'm trying to do is that I'm trying to make it so I can read the file by line, and then have a certain text added after the text display. As file read, yeah, that's for text files. These things are hard to search for. This might be useful. Python program is constructed from code blocks. A block is a piece of Python program text that is executed as a unit. Following are blocks, a module, a function body, and a class definition. Each command typed indirectly is a block. A script file, a file given as standard input to the interpreter, or specified as command line argument to the interpreter, is a code block. A script command, a command specified on the interpreter command line with the C option, is a code block. A module run a top level script as module main from the command line using M. Argument also is a block, this string. The string argument passed to built-in functions involve an access block. Code block is executing in an execution frame. Frame contains some administrative information used for debugging. Determines where and how execution continues after the code block's execution has completed. Naming and binding. So that's what I need. Sure, blah blah blah. I think that's not what I need. So I'm gonna close this one. Python's execution model, names and namespaces. Objects and classes. How to get all code blocks from a Python file. We need to understand the debugging system that is already built in Python. That way I can probably do what I want to do. I'll be right back. I really wasn't feeling like streaming today, to be honest. But now I'm kind of getting into it. I think you're stopped here. Execution model. I'm gonna read this stuff first. I think it was because of Christmas, kind of lost momentum. Because I just ate like trash. And yeah. It's a good reset though, I feel like. And this is not what I want. So I'm gonna keep reading the execution stuff. Naming and binding. Binding of names. Names refer to objects. Names are introduced by name binding operations. The following constructs bind names. Formal parameters to functions, class definitions, function definitions, assignment expression, targets. They are identifiers if occurring in an assignment. For loop header, after as in of its statement, except clause or the as pattern, instructional pattern matching. In the capture pattern, instructional pattern matching. Import statements. The import statement of the form from import star binds all names defined in the imported module, except those beginning with an underscore. This form may only be used at the module level. A target occurring in a del statement is also considered bound for this purpose, though the actual semantics are to unbind the name. You bind names to values and to modify attributes or items of mutable objects. Yeah, let me keep reading this. Each assignment of import statements occurs with a block defined by a class or the function definition or at the module level. A name is bound in a block. It is a local variable of that block unless declared as non-local or global. Name is bound at the module level. It is a global variable. The variables of the module code block are local and global. If a variable is used in a code block but not defined there, it is a free variable. Each occurrence of a name in the program text refers to the bindings of the name established by the following name resolution rules. Resolution of names. A scope defines the visibility of a name within a block. If a local variable is defined in a block, its scope includes that block. The definition occurs in the function block. The scope extends to any block containing within the defined one, unless a contained block introduces a different binding for the name. When a name is used in a code block, it is resolved using the nearest enclosing scope. The set of all such scope visible to a code block is called the block's environment. When a name is not found at all, a name error exception is raised. If current scope is a function scope and the name refers to a local variable that has not yet been bound to a value at the point where the name is used, non-bound local error exception is raised. If a name binding operation occurs anywhere within a code block, all uses of the name within the block are treated as references to the current block. This can lead to errors when a name is used in a block before it is bound. This rule is subtle. Python lacks declarations and allows name binding operations to occur anywhere within the code block. Local variables of a code block can be determined by scanning the entire text of the block for name binding operations. The global statement occurs within a block. All uses of the names specified in the statement refer to the bindings of those names in the top level namespace. Names are resolved in the top level namespace by searching the global namespace, i.e. the namespace of the module containing the code block, and the built-ins namespace. Namespace of the module built-ins. The global namespace is searched first. Names are not found there. The built-in namespace is searched. The global statement must proceed. All uses of the listed names. So pretty much everything is a name. And then you have the namespaces to dictate what is being used as a global variable and what is local. And the other difference is the built-in modules and the ones that are not. The global statement has the same scope as the name binding operation in the same block. The nearest enclosing scope for a free variable contains a global statement. The free variable is treated as global. Local statement causes corresponding names to refer to previously bound variables. The nearest enclosing function scope. Syntax error is raised at compile time. Name does not exist in an enclosed scope. Namespace for a module is automatically created the first time a module is imported. The main module for a script is always called main. Yeah, so this is the if name equals main stuff. Class definition blocks and arguments to execute and eval are special in the context of name resolution. Class definition is an executable statement that may use and define names. These references follow the normal rules for name resolution, with an exception that unbound local variables are looked up in the global namespace. The namespace of the class definition becomes the attribute dictionary of the class. The scope of names defined in the class block is limited to the class block. It does not extend to the block of methods. This includes comparison and generator expressions since they are implemented using a function scope. This means that the following will fail. Built-ins and restricted execution. See Python implementation detail. Users should not touch built-ins. Releasing strictly an implementation detail. Users wanting to override values in the built-in namespace should import the built-ins module and modify its attributes appropriately. Built-ins namespace associated with the execution of a code block is actually found by looking up the name built-ins in its global namespace. This should be a dictionary or a module. In the later case, the module's dictionary is used. By default, when in the main module, built-ins is the built-in module built-ins. And when in any other module, built-ins is analyzed for the dictionary of the built-in modules itself. Interaction with dynamic features. Name resolution of free variables occur at runtime, not at compile time. This means that the following code will print 42. So name resolution of free variables occurs at runtime. So it compiles first and then resolves. That's really interesting. So first it compiles this, then runs, then that's why it prints 42. Oh, it's because it's calling the function after this, that's why. Deval and exec functions do not have access to the full environment for resolving names. Names may be resolved in the local and global namespaces of the caller. Free variables are not resolved in the nearest enclosing namespace, but in the global namespace. The exec and eval functions have optional arguments to override the global and local namespace. This function supports dynamic execution of Python code. Object must be either a string or a code object. If it is a string, the string is parsed as a suite of Python statements, which is then executed. Be aware that no local yield and return statements may not be used outside of the function definitions, even if the context passed into the execution function. So what I need is, let me read this first. The arguments are string, non-optional globals, and locals. Provided globals must be a dictionary. Provided locals can be any mapping objects. The expression argument is parsed and evaluated as Python expression. What I need to do is understand the namespace. Names may be resolved in the local and global namespaces of the caller. Free variables are not resolved in the nearest enclosing namespace, but in the global namespace. Exceptions, oh, this is the end. Exceptions are a means of breaking out of the normal flow of control of a code block in order to handle errors or other exceptional conditions. An exception is raised at the point. Yeah, no, I don't think I'm not gonna read this. Oh, so that's a shame. I thought you would give me some functions or something. Structure of a program. This is just the whole file. Yeah, maybe it is impossible to do with Python. Now we need to use the C Python and stuff. Namespace packages. A namespace package is a composite of various portions. Each portion contributes a subpackage to the parent package. Portions may reside in different locations of the file system. Namespace packages do not use inordinalities for the path attribute. With a namespace packages, there is no parent init file. Yeah, that's not what I want. And this is not going. Categorize code objects from file, get source code for each of the objects. Categorize the files from source code. Hmm. Trying to think about what's the difference between creating a for loop outside of this function here on main. Oh no, a for loop here on main. For loop would read all the instructions here, but I'm not sure if I create a for loop here outside, it's gonna read the instructions one by one. It's probably gonna read. Yeah, it probably has to read all the lines, but yeah, the issue is that I need to get not only need to read the lines of the script, but get the operation that is being done. That's the issue. because I can't do that with an argument for obvious reasons. I don't know how to tell Python to do something every time it reads a line. I think I'll read this. I'm not sure if it's related, but it might have something useful. This, what I'm trying to do is probably not easy. It's definitely not easy because there isn't a lot of information out there, as I can see right now, but I think it's worth it. So I think the way that I'm gonna be able to do this is by looking at enough stuff that might be unrelated at first, but then I can piece them together eventually with enough time. Just trying to see if there's something that looks interesting here. Damn, there's a lot of stuff. A lot of stuff. Maybe I should search for how Python compiles code. That might have something that I can use. I think going through all of this is just a waste of time. Return a dictionary, exception, breakpoint, hook, debug, debug, malloc, stats. This function prints ref value, which is their standout, and saves value in built-ins. Return a frame object from the call stack. If optional integer depth is given, return the frame object that many calls below the top of the stack. It's deeper. Default for depth. Blah blah blah. Maybe if I use set trace, I put this stuff inside and see what happens. See if this runs. Curious to see if anything will happen out of this. I'm gonna make it equal to a variable and then print the variable. Just see if it prints anything. It turns an AC cook object which is similar to a named tuple of the farm. Hash info. This is a dictionary that maps modules names to modules which have already been loaded. This can be manipulated to force reloading of modules and other tricks. However, replacing the dictionary will not necessarily work as expected, and deleting session items from the dictionary may cause Python to fail. If one to iterate over this global dictionary, always uses cs.modules.copy or tuple to avoid exceptions as its size may change during iteration as a side effect of code or activity in other threads. So this was probably one of the reasons why the code wasn't working with NumPy, because it didn't make a copy. Also, it did run the function, but it didn't print anything. Let me print A and see what happens. Yeah, so this script calculates three mean absolute errors. So it's running, but doesn't print anything. Yeah, so here there is no copy being made of the sys modules, so that's a problem, like they say there. Path hooks, a list of callables that take a path argument to try to create a finder for the path. If a finder can be created, it should be returned by the callable. Path importer cache, a dictionary acting as a cache for finder objects. The keys are paths that have been passed through syspath hooks, and the values are the finders that are found. If a path is a valid file system path but no founder is found, then none is restored. I'm gonna be right back. path importer cache. Dictionary acting as a cache for finer objects. I think I already read that. Prefix. Set trace. Set the system trace function, which allows you to implement a Python source code debugger in Python. The function is thread specific. For a debugger to support multiple threads, it must register a trace function using set trace. For each thread being debugged, or use threading.setTrace. Trace functions should have the three arguments: frame, event, and arg frame. An arg. Frame, event, and arg. Frame is the current stack frame. Event is a string call line. Return exception or ROP code. So what is a stack frame? An object that tries to find the loader for a module that is being ported. I think I'm going to spend more than 2 hours here. Starting to get into it. Stack frame is a memory management technique used in some programming languages for generating and eliminating temporary variables. In other words, it can be considered the collection of all information on the stack pertaining to a sub-program call. Stack frames are only existent during the runtime process. Stack frames help programming languages in supporting recursive functionality for subroutines. A stack frame, also known as an activation frame or activation record. It's comprised of local variables, saved copies of registers modified by subprograms that could be restoration, argument parameters, return addresses. An individual stack frame has space for actual parameters, temporary location. So it's pretty much something that has the code that is being run. Should have three arguments: frame, event. Frame is the current stack frame, event is a string, call, line, return, exception, or OP code. Arg depends on the event type. Let me see. This is another script that Vivax did. This is .set trace. Also, he passed in the function that has the three arguments. So the question is, how do I keep track of the frame from one script in another one? Maybe if I search for how to get the stack frame of a script from another one. Trace function is invoked with event set to call. Whenever any local scope is entered, you should return a reference to a local trace function to be used for the new scope, or none if the scope shouldn't be traced. Local trace function should return a reference to itself, or to another function for further tracing that scope, or none should turn off tracing that scope. If there is any error occurred in the trace function, it will be unset just like set trace none is called. The events have the following meaning. Call. A function is called or some other code block entered. The global trace function is called. Argues none. The return value specifies the local trace function. Line, the interpreter is about to execute a new line of code or re-execute the condition of a loop. The local trace function is called. Argues none. The return value specifies the new local trace function. See objects for detailed explanation of how this works. Per-line events may be disabled for a frame by setting ftrace lines to false on that frame. Return a function or other code blocks about to return. Local trace function is called. Argues the value that will be returned or none if the event is caused by an exception being raised. The trace function's return values ignore exception. The exception has occurred. The return value OP code. The interpreter is about to execute a new OP code. See this for code details. This is assembler for Python bytecode. The local trace function is called. Argues none. The return value specifies the new local trace function. For opcode, events are not emitted by default. It must be explicitly requested by setting ftrace opcode to true on the frame. Note that as an exception is propagated down the chain of colors and exception events generated at each level. For more fine-grained usage, it is possible to set a trace function by assigning frame.ftrace tracefunc. It is possible to set a trace function frame.ftrace equals tracefunc explicitly, rather than relying on it being set indirectly via the return value from an already installed trace function. It is also required for activating the trace function on the current frame, which setTrace doesn't do. Note that in order for this to work, a global tracing function must have been installed with setTrace in order to enable the runtime tracing machinery. But it doesn't need to be the same tracing function. E.g., it could be a low overhead tracing function that simply returns none to disable itself immediately on each frame. For more information on code and frame objects, refer to the standard type hierarchy. Reason auditing events is that trace norms. The setTrace function is intended only for implementing debuggers, profilers, coverage tools, and the like. Its behavior is part of the implementation platform, and part of language definition. This may not be available in Python. Event type added ftrace lines and ftrace opcode attributes at each frames. So let me think for a second. So this would work for this script here, if it was on the same script. Frame events arg. It's hard to understand just from this explanation exactly how it works. If this does anything. Yeah, that's the problem. I put set trace at the end of this script. Let's see what happens here. I do like this. Bang. But then I will have to pass the frame. That's the problem. I just don't understand how it works. Also, I have to pass a function, I think. If I do just do like this, it's not gonna work. Maybe if I do it inside the trace thing. Oh no. If I call trace from here, and then here I call the other script, then I can pass in as a function. If it works. So this is gonna set the trace to this thing, which is gonna call the other function. Let's see. Oh, this is interesting. Seems like it's on a loop. Hmm. I don't understand why it's going a bunch of time. So it's printing the return here. That's why it's printing this stuff every now and then. And these mean absolute errors from the function. Maybe I should comment this stuff out so the output's cleaner on the other function. So it's printing the event call and the return. But it's weird that it's running, seems to be running the function a lot of times. Which I don't understand why it's doing that. It's on an infinite loop, it seems like. Just gonna wait a while to see if it stops or if it's just looping it forever. Yeah, so it did stop. Known type object is not callable. So it stopped just because it broke at some point. Yeah, but I think this is a start. You can pass in script here. And then here I can pass script equals this, and here call script. Yeah, I'm not sure how to pass a function as an argument. Let's see if this works. Now it's asking for arguments. So that's a problem. Maybe if I put it before here, it would work. Yeah, but I think it's gonna, yeah. I'm gonna search for videos about this.
So a stupid example is given here where we change the little prompt thing using sys. So if you want to see what this looks like, you can go into Visual Studio Code, or if you're using the interactive mode for Python, great. What I'm going to do is I'm going to open the
too much, so maybe that introduction to Python debugger has something useful.
Hey guys, welcome to the next video on Python tutorial for beginners. In this video, we will talk about a command line tool which is called PDB, which we use to debug our Python script. PDB, if I already have on these servers, you don't have the luxury of using an IDE. You will have to use the terminal in order to debug your Python script. And that's why I wanted to show you how to debug your Python script using the command line tool, which is PDB. Now to start with, I have this simple Python script which asks the user to input two numbers and these result into this key. You just need to kernel, or if you the path which my Python script on your operation of these two numbers in order to work with the command which you have. So this the P and this class, if you are using class, it's going to
It's not gonna have what I want. This module supports the analysis of CPython bytecode by disassembling it. The CPython bytecode, which this module takes as an input, is defined in the file include opcode.h used by the compiler and the interpreter. CPython implementation detail. Bytecode is an implementation detail of the CPython interpreter. No guarantees are made that bytecode will not be added, removed, or changed between versions of Python. The Bytecode Analysis API allows pieces of Python code to be wrapped in a bytecode object that provides easy access to details of the compiled code. Analyze the bytecode corresponding to a function generator, synchronous generator, coroutine method, stringer, or source code, or a code object. This is a convenience wrapper on many of the functions listed below, most notably get instructions, as is iterating over a bytecode instance yields the bytecode operations as instances. If first line is not known, it indicates the line number that should be reported for the first source line in this disassemble call. Class method from traceback. Construct a bytecode instance from the given traceback, setting current offset to the instruction responsible for the exception. Compiled code object, first line, the first source line of the code object. Return a formatted view of the bytecode operations, the same as printed by this. Info, return a formatted multiline. Return a formatted multiline string with detailed code object information that for the spy function generator. This module also defines the following analysis functions that convert the input directly to the desired output. It can be useful if only a single operation is being performed, so the intermediate analysis object is unuseful. Note that the exact contents of code info strings are highly implementation dependent and they may change arbitrarily. Print detailed code object information for the supplied function. Method source code string or a code object to file. We need shorthands for print. Over the instructions. Fantastic tool on the website. When you call a function, a frame is created for the local execution. Just gonna close this. You can close this one as well. I'll be right back. Yeah, I don't think this article is what I want exactly. It's probably a paid content. If they have content about it, about what I want. What's up, man? Snapchat? I don't have a Snapchat. Huh. I don't like social media in general. It's pretty bad for you. But the ones that are the most damaging are the ones that reinforce the short attention span, like Snapchat and TikTok and Instagram. Should probably stay away from them. I mean, do whatever you want, but probably not gonna be beneficial to you long term. So I'm thinking about ways to research stuff so I can understand how this shit's working.
Hello everybody, and today we are going to see the sys library. The sys library is related to the system and it has a lot of attributes and functions related to that system. So first, sys is a built-in library. You don't need to download it from external resources. And to import it, you just need to type import and sys. Let's see our first attributes. For the first one, we have platform. So to use this, you just need to type sys.platform. What is platform? Platform is a string containing a platform identifier. So, for example, if you are using Windows as a system, the platform will give you a string containing Win32. If you are using Linux, it will returns Linux, a string Linux. To print it, just print this, and you will get Linux and Win32 as output. For the second attribute, we have here copyright. So to use it, just type sys.copyright, and here, because it's an attribute, don't put two parentheses. You can use it the same way as the build number and platform. You can see all the copyrights here. And now we have two functions we will see. The first one is stdout.write, and this stdout refers to standard out. and it takes a string as a parameter. So what that do is giving an output also a string as a parameter, and the print statement. And as a parameter, it takes variable. And now for our empty, as you like, contains just one, as you can see, and hello, which we can. And let's check this. Emil. As you can see, this is a little bit of
Registers is traceback to the Python interpreter. Traceback is basically information that is returned when an event happens in the code. Might have seen traceback when your code has some error or an exception is raised. The register traceback is invoked when one of the following 4 events occur. Function is called, function returns execution of a line, exception is raised. Frame is the current stack frame. String each will be give their call. I just had an idea. I'm gonna test something. Let me see if this works. Doesn't work. Let's create our own local trace function with line function call events. These events are highlighted in the below given code. Local trace function which returns itself. Frame event argnon frame.fcall. Extracts calling function name. Extracts the line number. For in func name line number. Global trace function is invoked here and local trace function is set for fun. Global trace function is invoked here and local trace function. Turns reference to local trace function. My tracer. Huh. Might be wondering why does the local function my code returns itself. The reason is hidden in the functioning of this set trace. What this set trace does is thanks for the follow binary rip. Might be wondering why does the local function of my code returns itself. The reason is hidden in the functioning of this set trace. What this set trace does is that it first registers a global trace which is called whenever a frame is created, which returns our local trace function. So let me read that again. What this set trace does is that it first registers a global trace, which is called whenever a frame is created, which returns our local trace function, myTrace. I think it was meant to be myTracer there, instead of myTrace. So this creates a global scope with myTracer, which is the function here. whenever any of the above mentioned event occurs. For better understanding, look at the image shown below. Sys set trace registers global trace, invokes callback, returns local trace events, and return function call exception. If we don't want our scope to be traced, then none should be returned, but if that is not the case, we might want to do the same with our local trace function, then it should return none. Else, if there is an error, then set trace none is automatically called. There is a function named getTrace available in sys module to get a trace set by sys set trace. I still don't understand really well what's happening, but so far I think when it triggers our sys set trace, then it starts registering everything that came before that on the script. But it's not really clear. Global trace function is invoked here, and local trace function is set for fun. So these two activate the global scope and sets the local scope for the functions. Local trace function which returns itself returns reference to local trace function on my trace. So this returns the reference to here, which grabs this two. But there's a function named getTrace, which I also saw here. GetTrace. Get a trace function as set by set trace. Maybe if I inspected this stuff, I think I can go. I'm gonna go on the. Oh, but since it's built in, I'm not sure. Oh, I can open a file I have here. GetTrace. I'm gonna try to find the file. Use pretty print. It doesn't show the file. So maybe sys. I'll print this. How to find source code built in. Modules Python. To find out what file a particular module or function is implemented in, usually print file attribute. Alternatively, use the inspect module. For built-in classes and methods, this is not straightforward since inspect.get file and inspect.get source return a type error saying that the object is built-in. However, many of the built-in types can be found in the object's subdirectory of the Python source trunk. For example, see here for the implementation of the enumerate class. Still doesn't show how to get it. I want you to see how these functions work, so I can try to understand them better. Yeah, it's probably gonna be on C, so. But it shouldn't be impossible to understand. I feel like I already understand a little bit of C++. It's not that different from Python. I mean, it is different, but I think I can intuitively understand if I look at it. So I have the set trace and the get trace. Sys.get trace. Maybe if I just do the same implementation, but with get trace instead. Apparently, it's already giving me a mistake here. But weirdly, the set trace works. So I think what's happening is that the first time it doesn't work, and then for some reason starts working. Get trace typer takes no arguments when given. So let me stop this. So I think if I just put it like this, it's gonna find the trace that is being set here, but I'm not sure what it does exactly. So these, I don't know what they are, but from stuff that I've seen, it seems like it's the thread multiprocessing stuff. I'm not sure what a thread is also. I think is one of the blocks that is of the CPU, because each CPU nowadays has multiple blocks and each block executes code in memory. I think I'm gonna run this for more 2 hours. So it's giving me a bunch of stuff, but it's giving me the returns and the frame with F code. Let me I have an idea. I'm gonna erase this and see if there's any difference. Frame and file Anaconda threading pi. Huh. So now it's giving me the frame. Oh, so it's showing the execution scope. But I'm not sure what the sequence is. That's the problem. Not sure if this is the first time that it's going through. Because it seems that it goes way longer when I have this stuff on than when I just call the file directly. So I'm not really sure what the frame actually is. Oh, I have an idea. I'm gonna use inspect here, get source, func name. I'm gonna use this, and I'm gonna print this. Let's see what happens. So now I got a bunch of stuff. Dev shutdown. Nice. So I got the source here for one function. So maybe if I get the file instead, then I manually try to inspect them to see what's going on. I think it's get file instead of get source. Func name. File. And I think that's how the files are stored for each thing. But I might be wrong. Frame object has no attribute file. So how to get the location of frame object? sys.getFrame. Turn a frame object from the call stack. If not optional, if the optional integer def is given, return the frame object that many calls below the top of the stack. That is deeper than the call stack value where the default def is 0. Based on auditing event. Get profile, get trace. So let me go back here. I'm gonna comment this for now. And try to do get frame. I think it's like this. Slash get frame. Oh, it has def as well. Huh. So I think depth is how many frames back I want you to look at. Return a frame object from the call stack. If optional integer depth is given, return the frame object and many calls below the top of the stack. If that is deeper than the call stack, oh, I think I remember what a stack is. So stack is basically the way that the computer organizes memory. So each time a code block is executed, it goes into the call, into the stack, which is just a pile of memory instructions. Oh, now I remember. And then it piles all of them up, and then in compile time, and then in the execution, it starts reading them and taking off the stack. I think first it goes through the CPU, which is the thread, then it goes through the stack, which depends on the memory that is being used. Yeah, I think that's how it works. There was a video, I think, this year that explained this. I think it was on this one. No, it was this one. No, it's probably operating system. I think it was on the other one. I'm gonna watch these videos again just to refresh my memory. But I think I'm on the right path here. So it's probably gonna be easier to use the inspect module and call it like this, and then I just call it manually. Maybe I can make this equal to a variable. And then, yeah, but then I was thinking about making this equal to a variable outside of here. Yeah, that might be possible. Because then instead of changing inside the function, but it's just a detail anyway. I think first I have to concern myself in getting what I want out of this. What is f locals dot items? Go here. Oh, there's built-in here. Zero origin. Where coroutine was created or none. This set coroutine origin tracking depth. Origin name of this function or method. Qualify name. So what do I want? F locals. Local namespacing by this frame. Global namespacing by this frame. Yeah, but I think this is the correct way. You call here. I'll be right back. think I'll read something while I watch those videos. Then I'll go back to trying to figure this out. Source code for building vital functions. It's probably gonna be on C. This is module. The built-in functions definitions. I think what I need to do is just understand better how set trace works, because it seems that it is what I want, but I don't understand it really well. So it provides me a path to getting what I want, but it's not clear how the execution works. So it's not clear in my mind how to connect the things the way that I want them to be connected. Oh, return trace. Huh. So this is recursive. That's why it was on a loop. So maybe I should return something else here. But that's the thing that I don't understand is when does this start and when does it end? And what exactly is going through this once I call the function? Because I think the normal way that it is used is for specific functions inside of a script, not for a script itself. Yeah, let me watch the video and need some stuff. These videos here.
This diagram illustrates the essence of a segmented memory management system.
Yeah, this is gonna talk about the call stack and that stuff.
On the left are some of the programs that have been installed on the computer's hard drive. These are just files on disk until they've been launched. In the middle is the computer's physical memory, the RAM. This contains any programs and data that are currently in use. On the right is a swap file on the computer's hard drive. Each program that's currently running might be a procedure or a function. A running instance of a program is called a process. Needless to say, the operating system itself has a number of processes in memory when the computer is working. Suppose the user starts launching applications. Sooner or later, the memory is going to fill up. Notice how different processes occupy different amounts of memory. These portions of memory are known as segments. They're based simply on the sizes of the programs. For each process, the operating system knows its starting location and how big it is, so it knows where everything is. When a request is made to launch some more software, perhaps a word processing application, something has to move out of memory to make room for it. If one of the processors belonging to the presentation software is currently doing nothing, the operating system might decide to move it to disk, temporarily at least, so the word processing programs can begin. When another request is made, perhaps to launch a web browser this time, another idle process of at least equal size has to be moved out of memory to make way. In order for the spreadsheet process in the swap file to start running again, something else of at least equal size has to be swapped out. Although there is enough free space to allow for this, the free space is fragmented. In a segmented memory management system, each process is atomic. It can't be split up. It's all or nothing. So the spreadsheet process is going to have to wait. The chances of the large presentation process getting back into memory are now particularly low, because a number of adjacent processes will have to become idle before this can happen. In summary, in a segmented memory management system, segments are swapped between disk and main memory as needed. Program segments correspond to blocks of program code, such as procedures or functions. Data segments correspond to data structures.
This guy talks really slowly, so I'm gonna put this on 2x. I'm not sure if I'm getting used to this, but because nowadays most of the videos, even on 2x, seems like really slow to me. Not sure if I'm getting used to it or if it's just those videos. Just these people that talk really slowly.
Structures such as stacks, queues, or graphs. Segments vary in size. The operating system knows the start and size of each segment in physical memory. Each segment is atomic. Either the whole segment is in RAM or none of the segment is in RAM. A segment in memory can only be replaced by a segment of the same size or smaller. Segmentation can result in memory fragmentation, a lot of small segments with gaps in between. Large segments may not be allowed into the memory very often at all. Segments can be pushed together to limit the amount of fragmentation and allow large segments to be loaded more often. With paged memory, as far as any one program is concerned, it has the whole memory to itself, which of course is not true. But the operating system allows the program to behave as if this is the case. A program's view of the memory is called logical memory. In reality, each program is broken up into a number of equal-sized pages. Each page is only 4 kilobytes in size, so a single page might contain a single program, more than one program, or just part of a program. These pages could be anywhere in physical memory that the operating system decides to put them. Indeed, some pages may be on secondary storage. To make this possible, the operating system maintains a page table with information about which logical locations map to which physical locations. As far as any one program is concerned, the memory is a quiet place. Here's the word processor's view of the memory, if it is also running. And here's what the spreadsheet application thinks is going on. The reality of physical memory is, of course, somewhat more complicated. When yet another program, or indeed data, wants to access the memory, it may well be loaded in a fragmented state. If there isn't enough space, some of the other pages will be moved to disk. This is called paging out. When a program on disk is required again, it will be paged back in. Supplementing the RAM with secondary storage like this is called virtual memory. In a busy system, when the memory is almost full, there can be so much paging activity that the computer becomes unusably slow. This is called disk threshing or disk thrashing. In summary, with paged memory, the memory is split up into small, equal-sized sections called pages or page frames. A single application might occupy multiple pages, which aren't necessarily contiguous. Each application program has its own view of the memory. This is called logical memory. A page table records where the different pages of a program are located in physical memory. Unused pages may be paged out to a swap file on disk to make room for others, and these pages are paged back in when they're needed again. Supplementing physical memory with secondary storage is known as virtual memory. When memory is low, excessive swapping can lead to disk threshing, and this can degrade performance. So what's better, segmentation or paged memory? Segmented memory makes an entire block of code available to the processor, which allows for fast access. Segmentation, on the other hand, can lead to fragmentation of free space. With segmented memory, large processors might not get access to the memory very often.
The call stack is a dynamic data structure maintained inside the computer's RAM by the operating system. Its purpose is to control the way procedures and functions call each other, and to control the way they pass parameters to each other. A call stack is maintained for each task, and indeed for each thread. It's sometimes referred to as the machine stack, or the execution stack. More often than not, it's simply known as the stack. Consider a scenario where procedure 1 calls procedure 2, which in turn calls procedure 3, which in turn calls procedure 4. Let's suppose also that procedure 2 has 2 input parameters, and so does procedure 3, and so does procedure 4. Also, procedure 2 declares 2 local variables, as does procedure 3 and procedure 4. So what happens when procedure 1 calls procedure 2? First of all, any parameters which procedure 2 is expecting are pushed onto the stack. They're pushed onto the stack in the reverse order to which they were declared in procedure 2's parameter list. Next, the return address of procedure 1 is pushed onto the stack. This comes from the CPU's program counter, and it will be used later to return control back to procedure 1 when procedure 2 is finished. It's sometimes called the instruction pointer. Now that procedure 2 is in control, any local variables declared inside procedure 2 can be pushed onto the stack as well. So at this stage, procedure 2 is up and running, and it has what's called a stack frame. Procedure 2 can traverse this stack frame to get a hold of any data it needs. Suppose now that procedure 2 calls procedure 3. As before, any parameters which procedure 3 is expecting are pushed onto the stack. Next, the return address of procedure 2 is pushed onto the stack. This comes from the CPU's program counter. Finally, any local variables declared inside procedure 3 are also pushed onto the stack. So procedure 3 is now in control, and its stack frame is in place so it can get a hold of any data it needs. When procedure 3 calls procedure 4, we see the same steps again. Any parameters which procedure 4 is expecting are pushed onto the stack one by one. The return address of procedure 3 is then pushed onto the stack, followed by any local variables which have been declared inside procedure 4. Procedure 4 is now in control. When procedure 4 has finished, the stack will be torn down. So, procedure 4 is now returning control to procedure 3. First of all, any of procedure 4's local variables are popped off the stack. Procedure 4 can then pop off the return address to repopulate the program counter and return control back to procedure 3. In this particular scheme, procedure 3 is responsible for cleaning up the rest of procedure 4's stack frame. So procedure 3 is now back in control and it can pick up from where it left off. When procedure 3 returns control to procedure 2, we see the same again. Any local variables are popped off the stack. This allows procedure 3 to pop the return address off the stack, and procedure 2 is back in control. Procedure 2 cleans up the stack and continues from where it left off. As before, when procedure 2 is ready to return control to procedure 1, local variables are popped off the stack, procedure 1's return address is obtained, the program counter is repopulated, and procedure 1 is back in control. It cleans up the stack and picks up from where it left off. So here we are, back where we started. In the scheme we've just described, we've seen that procedure 2's parameters are pushed onto the stack before the return address of procedure 1 is pushed onto the stack. And hence it's the responsibility of the calling procedure to clean up the stack once it's regained control. In some literature, you will see that the return address is pushed onto the stack first, before the parameters. The way this actually works depends very much on the machine architecture, and of course the machine language. It's also worth saying a little bit about how functions return their values. Again, depending on the architecture, function return values may be passed back to the calling procedure via the stack. Alternatively, they may be passed back via a CPU register, specifically the accumulator. So if you read around this subject, the waters may be a little bit muddied, but it's worth appreciating that exactly how it happens very much depends on the design of the central processing unit and of course the...
Another thing that just hit me is that on that code, the Vivax didn't specify all parameters here for line, return, exception. Just use the call, I think, if I'm not mistaken. Yeah, if event equals call. I think I'm gonna take this off. I'm gonna put line here. Func name equals frame. Line name. Equals OP code, I think. OP code. Name equals frame. So I think this should show me line by line what's happening, because call only shows the functions and line shows the code, shows each line. Function is called or some other block, code block entered. The global trace function is called, arg is none. Interpreter is about to execute a new line of code or re-execute the condition of a loop. Local trace function is called. The local trace function is called. Arg is none, the return value specifies the new local trace function. See objects, out note tabs for a detailed explanation of how this works. So this is on the page there. Oh, here it is. Description of the internal format of the line number table. Conceptually, the line number table consists of a sequence of triples, start offset, end offset, line number. Note that not all bytecodes have a line number, so we need handle done for the line number. However, starting the above sequence directly would be very inefficient, as we would need 12 bytes per entry. So it's pretty much a table with bytecodes. The code is as follows: def colons and 0 table. To a first approximation, we want to call the tracing function when the line number of the current instruction changes. We're computing the current line for every instruction is a little slow, though, so each time we compute the line number, say the bytecode indices where it's valid. It's true so long as execution does not change lines, that is, holds the first bytecode index of the current line. However, we don't always want to call the line trace function when the above test fails. Which compiles to this. So it's pretty much a table with bits, with bytes. Per line events may be disabled for a frame by setting ftrace lines to false on that frame. A function or other code block is about to return. The local trace function is called. Arg is the value that will be returned, or none if the event is caused by an exception being raised. The trace function's return value is ignored. Maybe on the return, I should just do trace frame to change the frame. A return. So I call the function again with a different frame, which is the one that is being returned. If that does what I think will do, it will, once the code reaches a return in the other script, is gonna change the tracing to whatever that return was. But the issue with that is that's probably not gonna, it's gonna make the trace deviate from the main script and go into the other scope of the function of that script. But I'm not sure if that's what it does. Args format for key values in func name, args format. I think I can erase this for now. Maybe I'll put it back eventually. I think I'm gonna read about how the sysset trace works more, so I understand the direction it's going. It's about to execute a new OP code. Local trace function is called, but there's an exception. For more fine-grained usage, it's possible to set a trace function by assigning frame.ftrace equals tracefunc explicitly, rather than relying on it being set directly via the return value from an already installed trace function. This is also required for activating the trace function on the current frame, which setTrace doesn't do. Oh, so this activates the trace function on the current frame. So maybe I should put this here and here, right? So this is gonna make the maybe you should do the other way around. Yeah, frame equals frame.ftrace, which is gonna make this is trace be executed on this frame, and then I can call it again. Yeah, but then why is it not showing like this? I think this works, but since Python is open source, you can read the source code to find out what file a particular module or function is implemented in. You can usually print the file attribute. Alternatively, you may use the inspect module. Use a cookbook and search for supplement queries. See, Python has moved to GitHub and the Mercurial repository. Install git necessary git clone. Let's say we're looking for the definition of a print. How to locate the sys module folder in Python. In the computer, actually. Which returns a string. Sys.path. This path is a built-in variable within the sys module that returns the list of the directories that the interpreter will search for the required module. When the module is imported within Python file, the interpreter first searches for the specified module among its built-in modules. Not found, it looks through the list of directories defined by syspath. It's probably not what I want. It's probably on side packages, but it's weird because it's built in, so makes me think that is on another file. So this is the matplotlib thing. So let's see. Simp. Simpi. Yes, it's not here. Oh, so I'm not on side packages. Oh, so there's 2 side packages? That's weird. Maybe there's 2 environments on this project. Yeah, no C's here. We just saw trace. Find lines from code. Not true if it should count number of lines. I'm not sure if that's... Oh, sys trace. Set trace. Adds information about who called who to the self callers dictionary. The code block being entered is to be ignored, return none. Returns none. Always returns self.local trace. Old frame file name. Oh, so here it is. Huh. So this is very similar to the function that Vivex did. Maybe I should save this stuff here. Yeah, I'll put this. I'm gonna put this function here somewhere. Probably here. Handler for call events. If the call block being entered is to be ignored, returns none. Self.local trace. So this is supposed to go into the call thing. I guess. Not really sure, but maybe I should put frame here. Not sure what this does, but oh, traceback here. Huh. If it doesn't work, then I'm gonna. If it doesn't show anything or is not what I want, I'm just gonna comment out and test some stuff from it. So I guess these files that don't have a directory are probably from Python modules, built-in modules. But I might be wrong about that. And this apparently is the set traceback function. Oh, it has to be on. It can't be this one. It has to be on a file called a directory called sys in order to be accessible with the dot notation. But that doesn't make much sense because they can't find the sys file here as well. No, this is the built-in modules, I think, here. You have JSON logging, multiprocessing. So I guess sys is just the library root, probably. And that is the traceback function that is being accessed to sys.traceback. Formatting and printing list of traceback lines. Print list. Print a list of tuples as returned by extractdb or extract stack as a formatted stack traced to the given file. File is known, file equals sys, standard error. Parting stack summary from list extracted list. Print item file. Format list. Format a list of tuples or frame summary objects. For printing, I think I'm gonna. I'll be right back. I'll close the curtain and get more energy drinks. So where was I? I think here. Print option limit stack trace entries from the traceback TB. Limit is omitted or none. All entries are printed. Files omitted or none, the output goes through C standard error. Otherwise, file should be an open file or file link like object with a write method. So this is interesting to test. A shorthand hand for format list, extract TB limit. Just don't understand how these things go together. What is these arguments? Doesn't make much sense. Printing and extracting traceback. So TB should be traceback. Return a stack summary object representing a list of preprocessed entries from traceback. This is useful for alternate formatting of stack traces. Limit is omitted or none, all entries are extracted. Preprocessed stack trace entry is a frame summary object containing attribute file names. Attributes file name, the Nino name and line representing the information that is usually printed before a stack trace. The line is a string with leading and trailing whitespace stripped. If the source is not available, it is none. Turn stack summary extract. Oh, so this is the messages that I get when something is wrong with the code. Format the stack trace and the exception information. The arguments have the same meaning as the corresponding arguments to print exception. The return value is a list of strings, each adding in a new line and some containing internal new lines. Not official API, but folk probably use these two functions. Print exceptions use execute info. Print a stack trace from its invocation point. The optional f argument can be used to specify an alternate stack frame at which to start. The optional limit and file arguments have the same meaning as for print exception. Maybe if I call this inside of the other function and I pass the file that I want as an argument. Extract the raw traceback from the current extract frame. The return value has the same format as for extracted B. The optional f and limit arguments have the same meaning as for print stack. Each item in the list is a quadruple file name, line number, function name, text. And the entries are in order from oldest to newest stack frame. If f is none, f equals sys get frame f back. Let me see what is this f back. Next outer frame object, this frame's color. So if it's none, just guess the previous one. Stack equals stack summary dot extract walk stack f. Stack reverse. This reverses probably. Which one shows first? Clear all references to local variables in the frames of a traceback. Frame summary. A single frame from a traceback. Attribute file name, the file name for the frame. The line within file name for the frame that was active when the frame was captured. Name the name of the function or method that was executing when the frame was captured. Line the text from the line cache module for the off code that was running when the frame was captured. Locals, either none if locals were not supplied, or a dict mapping the name of the wrapper of the variable. What is this lots? What is the purpose of slots, especially with respect to when I would want to choose it? Python 1 is supposed. The special attribute slots allows you to explicitly state which instance attributes you expect your object instance to have, with the expected results: faster attribute access, space savings in memory. Storing value references in slots instead of dict. Deny dict in weak graph. Creation if parent classes, deny them, and you declare slots. You should only declare a particular slot one time in an inheritance tree. For example, within the fooling bar. Python doesn't object when you get this wrong. Files might not otherwise manifest. This is because the basis slot descriptor has a slot separate from the wrongs. So you should only declare once for the parent class, not the other ones. To have attributes named in slots to actually be stored in slots instead of a dict. A class must inherit from object automatic in Python 3D. To prevent the creation of a dict, you must inherit from object, and all classes in the inheritance must declare twice use slots faster attribute access. The creator of Python states that he actually created slots for faster attribute access. It is trivial to demonstrate measurably significant access. Another purpose of slots is to reduce the space in memory that each object instance takes up. I'm not sure if I really understand it, but whatever. So initializes with file name, lineal name, lookup line. Lookup line if true line cache is considered for the source code line. Otherwise, the line will be looked up when first needed. Locals if supply the frame locals, which will be captured as object representations. Line if provided, use this instead of looking up the line in the line cache. Self-doc locals equals k reprove for k v in locals dot items. If locals else none. So it creates a dictionary with the string representation of class for locals items. Which is a property of this class. Locals. So when he's getting the frame, he's gonna get the items of the frame and put them on a dictionary with the item and the string. I guess this is what this does. And if there is no items, then maybe none. If instance other frame summary, return self file name equals other dot file name. So let me check what the equals does again. God damn, man.
Machine language. What's important here is to realize that parameters are passed via the stack, and that return address is crucial to return control back to the calling procedure.
Hey everyone, in this video we're going to be overriding the EQ method or the equals method so that we can compare books. So when is this method going to be used? Well, let's say we have two books, which we created two books here, and we say book is equal to book 2. So we're comparing two book objects, and running this, it's going to be false. The default behavior of the double equals when working with our custom objects is to see if the books are the same area of memory, the same exact object. So in order for that to happen, we would have to set book 2 equal to book. And now we get true. However, I don't really like that implementation. I'd much rather prefer it compare it by title and page number. So in that situation, it's going to be where we have two books, but let's just say they have the exact same data. Are you my mother? Printing it now, we get it to say false. However, I want it to be true in this situation, because in my brain, these are the same books. Your brain. So what we do is we override, let's make sure we're at the right indent, underscore underscore EQ, and this is going to have self as a parameter. But not just self, it's going to have another one, which is the thing we're comparing against. So I'll just call that other. So in here, we can return true if they're equal or return false if they're not equal. So let's just check if self.title is equal to other.title, and we're also going to check the pages. So self.pages is equal to other.
I think I get it. Just show override to make it equal when comparing different ones. It's still hard for me to understand though how this actually works. Block a stack yielding the frame and line number for each frame. This will follow f.fback from the given frame. If no frame is given, the current stack is used. Usually used with stack summary.extract. So let me see something. This stack summary is called a lot here. Assume it's a class. Maybe it's not on this file. Or maybe it's declared later. So if f is none, it goes back. And y is not none, it's gonna create a generator with f and f Lino line number probably. F equals f.f back. Block a traceback yielding the frame and line number for each frame. This will follow tb.tbnext and thus is in the opposite order through block stack. Usually used with stack summary.extract. While tb is not done, yield tb.tb frame, tb.tb line number, tb equals tb.next. So I guess these functions show all the stacks, gets the current stack, and then generates all the other stacks before the one that is the current one. That's what I assume this does. And this gets the frame, this gets the line number. Class stack summary. A stack. Oh, that's the stack summary thing. A stack of frames. So this, it's weird that it is declared after all the other ones. It feels like it should be much easier to read if those classes were declared before, in the beginning of the file. Maybe there's a reason for that I just don't understand. Class method def extract. Create a stack summary from a traceback or stack object. Generated the yields frame line number tuples should include in the stack. None should include all frames or the number of frames should include. If true, look up lines for each frame immediately, otherwise look up until it's rendered. Limit is none, limit equals get attribute, sys traceback limit none. Limit equals 0. Frame generation. The class of names equals must defer line lookups until we have called check cache. I'm gonna look up what is a lazy cache. Python. The line cache module allows one to get any line from a Python source file while attempting to optimize internally. Using a cache, the common case where many lines are read from a single file. This is used by the Traceback module to retrieve source lines for inclusion in the formatted traceback. Tokenize.open function is used to open files. This function uses tokenize.detect encoding to get the encoding of the file. In the absence of an encoding token, the file encoding defaults to UTF-8. The line cache module defines the following functions. Line cache.getLine, get the line number from file name, named file name. This function will never raise an exception. It will return empty string on errors. If a file named file name is not found, the function first checks for loader in module globals. There's search a loader and it defines a getSource method, then that determines the source lines. If getSource returns none, then empty string is returned. Finally, if file name is a relative file name, it is looked up relative to the entries in the module search path. Choose.path. Clear cache. The cache. Use this function if you no longer need lines from files previously read using getLine. Check the cache for validity. Capture enough detail about a known file-based module to permit getting its lines later via getLine, even if module globals is none. Delay call. This avoids doing I/O until a line is actually needed, without having to carry the module globals around indefinitely. So this is the same page. So this class calls the other class. Yeah, this is super confusing to me. Don't understand what's going on at all. Frame summary, file name, line number. For filing F names, line cache.check cache file name. Immediately lookup as desired, trigger lookups now. Create a stack summary object from a supplied list of frame summary objects or old style list of tuples. While doing a fast path check for each instance is appealing, run cleanup, traceback, and others. Similar code may break this by making arbitrary frames. Plain tuples, so we need to check on a frame by frame basis. Format the stack ready for printing. Returns a list of strings ready for printing. Each string in the resulting list. The single frame from the stack. Each string ends in a new line. Contain new lines as well. So I get that this is for the traceback stuff. It's probably the classes are created, but I don't understand. I think the issue is I don't understand really well when to build the class to do the traceback and how to build it. For example, let me see here. It says list here, but when is this created? And here there's these names for the frame summary. So we have the file name, the line number. Maybe if I create this on a loop. The thing that doesn't make sense is that there's file name and line number. So maybe I can create for lines in line in. Yeah, but then it doesn't make sense. Yeah, I don't understand this at all. Module is a traceback object. This is the object type that is stored in the sys.last traceback variable and returned as the third item from sysexecute function. So I think this last traceback is somewhere here, if I'm not mistaken. I remember reading this somewhere here. Maybe it's just one of the functions that uses this, but it's not here. I can't find it. So the module defines the following functions. Traceback.printtb. Oh, so this is the documentation of the file that I'm reading. Probably. Yeah, so the set traceback is probably a different file. So set trace. freedom to limit stack trace entries from traceback object DB, starting from the caller's frame. Limit is positive, otherwise print the last absolute limit entries. None. If files omitted or none, the output goes through string center. Otherwise, it should be an open file or file-like object to receive the output. It still doesn't specify anything. It's like the description doesn't make it easier to understand how to use this stuff. Maybe I'm just dumb, but this is what I have open there. I'll be right back. I think what's happening is not that it's so difficult to understand, it's just that I'm trying to relate this to what I'm trying to do, and then it gets confusing because I'm not really clear on how it works that well. I think I can close this. That doesn't make any sense. Everyone in the software industry knows Kent Beck, the pioneers of extreme programming and test-driven development and the co-author of JUnit. One of his lesser-known projects was JUnit Mass, which aims to reduce the time developers have to wait while one of these Python model is better is included. This is manifested in many Python standard library modules, such as ASD, source code parsing, and this bytecode disassembly. One of which is the ability to make the Python interpreter call an external function whenever a line of code is being executed. You can do a lot of fun stuff with it. For example, coverage.py uses this to build code coverage data. PDB uses to insert breakpoints into a running application and change the way a Python program is executed. How can it be used? For nostrils, we need to write a nose plugin that installs a trace function when a test is encountered. The trace function records the line number and the current test case name. After all tests are run, we have our map. Simple use case. To start, we need a simple use case. This is the code under test. Part worker test. As you can see, you have 4 tests and 2 methods under test. The goal is that when running no set tests, nostrils is a switch, blah blah blah. On maps. Nose plugin. I won't go into the detail about how to create plugin for nose. Now let's have a look at the trace function. Event line, soft trace down, frame, soft trace. Okay. A trace function should take 3 parameters: frame, the current frame, object, event, what type of event that triggered the trace function. See here, args, and any additional parameter. Here I'm only interested in the line event, which is triggered when a new line of code is being executed. When this happens, we invoke trace down. which walks the frame stack by recursing on frame.fback. When it's done, we are at the bottom of the stack. Because we're tracing the execution of tasks, we'll probably stop traversing when the code object of the frame is the entry point of the task case. Save ourselves some unnecessary traversal. So this is unnecessary in my case, I think. I can just put this 2 last lines here. There's a few there's are few things we need to collect. File name, line number of the code being executed, and the task case name that covers the code. The data structure we use here, the dictionary of dictionary at the top level, the keys are file names, and the values are dictionaries of with keys and line numbers. The value is the set of task case names. We have a prototype of what could become potential problem scale. I'm only running nostrils on trivial code base. Refactor the code, revise the instruction published. Also, this is just for the thing. I think I'm gonna copy this traceback function into my own thing. It trace down. And I don't need the song. Maybe I'll just put it outside of here. Oops. Yeah, this is probably all I need. So this apparently is a problem. Monday. There we go. So here it also returns recursively. Shorthand for print exception. Preemption limited stack trace entries starting from the invocation point. Limit is positive, otherwise printed less absolute limit entries. If limited is omitted or none, all entries are printed. The optional F argument can be used to specify an alternate stack frame to start. Maybe I can use traceback.print stack here. Can do this on all of them. Return a stack summary object representing a list of preprocessed stack trace entries extracted from the traceback object TB. It is useful for alternate formatting of stack traces. The optional limit argument has the same meaning as for print TB. A preprocessed stack trace entry is a frame summary object containing attributes file name, line number, name, and line representing the information. It is usually printed for a stack trace. The line is a string with leading and trailing white space stripped. If the source is not available, it is none. Extract the raw trace back from the current stack frame. The return value has the same format as for extract_db. The optional f and limit arguments have the same meaning as for print stack. Present a single frame in the traceback or stack that is being formatted or printed. It may optionally have a stringified version of the frame's locus included in it. Source code is not looked up until the frame summary has the line attribute access. So examples. The following example demonstrates the different ways to print and format the exception and traceback. But here is only printing on the exception. That's the problem. The following example shows the different ways to print and format the stack. I think it just hit me that I could create a class for this, and then I can create a decorator function. And then I can create an object. I can create an instance of the class that takes the script that I'm trying to review, and then make the class so that the decorator wraps the script with the traceback function that I'm building there. That way I can pass the script as an argument instead of having to directly put as an argument of the function. It's still unclear to me when this starts working. I think so far from what I read, it seems that it works. It just gets the executions that happen until the point that the traceback is called. But I'm not really sure if that's how it works. Walk a stack following an FF back from the given frame, using the frame line number for each frame. If F is none, the current stack is used. This helper is used with stack summary.extract. Walk a traceback following to be next, yielding the frame and line number for each frame. This helper is used with module also defines the following classes. So it's exactly the explanation of the file I was reading. Construct a stack summary object from a frame generator, such as is returned by walk stack or walk to be. 20 frames. Construct a stack summary object from a supply list of frame summary objects, row style list of tuples. Turn list of strings ready for printing. Each string in the resulting list corresponds to a single frame from the stack. Each string ends in a new line. Represents a single frame in a traceback plus traceback. Traceback, the frame summary. Represents a single frame, the traceback or stack that is being formatted or printed. It may optionally have a stringified version of the frame's locals included in it. If lookup line is false, the source code is not looked up until the frame summary has the line attribute accessed. Which also happens when casting it to a tuple. Line may be directly provided and prevent line lookups happening at all. Locus is an optional local variable dictionary. Let me run this and just see what happens. Frame object is no attribute get frame. So I'm just gonna erase this for now. This is probably because I changed some of the code. There's no attribute there. Trace. So I think I'm gonna erase this stuff. See now what happens. Line 15. So what's going on? So I guess it prints on red? Don't understand. It's clearly not an error because it continued running. Hmm. I think these are Python files. Uh, some of the built-in modules. The following diagram and text describe the data flow through the system. So process pool executor, work IDs, work items, local worker thread, call, result queue, process pool. That's interesting. Reads work IDs from the work IDs queue and looks up the corresponding work item from the work items dict. If the work item has been cancelled, then it is simply removed from the dict. Otherwise, it is repackaged as a call item and put it in the call queue. New call items are put in the call queue until call queue is full. Workers are created as daemon threads and processes. This is done to allow the interpreter to exit when there are still idle processes in the process pool executors process pool. A shutdown was not called. However, allowing workers to die with the interpreter has two undesirable properties. The workers would still be running during interpreted shutdown, meaning that they would fail in unpredictable ways. The workers could be killed by evaluating a work item, which could be bad if the callable being evaluated has external side effects, e.g., writing to a file. To work around this problem, an exit handler is installed, which allows the workers to exit when their work queues are empty and then waits until the threads process finish. So this is threading, global trace. Handler for call events. If the code block being entered is to be ignored, returns none. Else returns self.local trace. This was the stuff that I was reading before, so I don't think it's this file. Oh, this is the other file I had open. A boolean value indicating whether this thread is a daemon thread. This must be set before start is called, otherwise runtime error is raised. The initial value is inherited from the creating thread. The main thread is not a daemon thread, and therefore all threads created in the main thread default demo equals false. Entire Python programs exits when only demo threads are left. As the property decorator, so is a property of this class. Which is the thread class. Let me run this again. I think I'm just gonna wait until it breaks somehow. Just see if it breaks. Maybe instead of the print stack, I should get the stack instead. Yeah, now it's showing different stuff. But this is really interesting because it's allowing me to see more how Python actually works. And now it's finished. Exception ignored in function walk value dictionary. Was recently call last. Yeah, it was the same thing that I stopped before. Non-type objects not callable. Yeah, I guess it calls this once the script stopped running, maybe. Let me try to do the, where was it? Here. Extract stack. Extract the raw traceback from the current stack frame. And it seems like it's only hitting the line 15. Or at least hits that the most, which is this one. So it means that it usually is a function that is being called and not an event. I don't see line 22 here. The other lines are for other programs. The processing, multiprocessing, logging, and thread stuff. And I guess this is related to the script that I'm running because it probably runs this every time that a script is run. But I don't see the functions from the actual script. That's the problem. Because it should show at least some of these functions here. Meaning absolute error, the train test split, XGB booster, XGB regressor. Because ultimately that's what I want. I want that you get these libraries and the functions. So threading, I had it open. Zutio. And this is the multiprocessing stuff that is opening. Let me print func name dot. So this is a frame. So I should be able to use this stuff here. Next outer frame object, next inner traceback object, built-in's namespace seen by this frame, code object being executed in this frame, f.code. Should be possible to do this. And then f globals as well. Just press Ctrl D to copy the line. At least in PyCharm. Yeah, now it's showing me a bunch of stuff, which is good. But let me stop this and see if extract stacks is giving me anything. Huh. Okay, at least I'm getting new stuff. Yeah, so this extract stack doesn't print anything. I assume it does the same thing as the print stack, but instead of printing, you just get the stack. Maybe I have an idea. I'll create a list here, and then I'll push this dot append, and then I'll print the list after this, and see if it's gonna be printed. I'll be right back. So let me run this now. It's giving me an empty list. And now it's not showing anything here. So let me do this instead. So I guess when it keeps running, it's not because it's calling multiple times, it's just going through the whole script maybe. And then, because I'm not returning anything here. So it can't be, oh, I'm returning here. The return thing. Let me run this. Yeah, but now it's showing me this stuff. Line 17. So when he runs this, he's just printing the execution. I guess. Yeah, so I guess it just runs through the script and then prints the everything. Let me comment this out and see how long. Yeah, so I have print stack on both of these, so it means that it's never hitting this if statements here. And it's never hitting this if statement as well. Otherwise it would be printing the stacks each time. Now let me see this. It's weird that it's just calling the processes of Python and not the script. Now I have an idea. I'm gonna run the same command on this file. Not this file. This file. I'm gonna run both of them simultaneously. And then I'm gonna do this for this one as well. Oh, the problem is that I need a frame there. Frame event and arc. So let me just, yeah, but then it's not gonna print anything. The thing is, I don't think the other script is calling this one. That's the problem. Take 0 position argument, but 3 were given, so. Maybe if I just do the same thing that I did here. And I'm just gonna comment this out for now. Put this here. And then I can do the print statement as well. Right. Now let me run this. Ah. Oh. It's here. I want to see if they're different. It looks like they are. Also, it's calling the same stuff. Weak ref, multiprocessing, logging. But this logging, I don't think the other one was calling. Oh, apparently it is calling now. So maybe this is running the main function. It's doing the same thing. IO parser. Yeah, I don't understand what's going on. It's probably gonna take me a while until I be able to do what I want to do. SetTrace is an inbuilt method of threading module in Python. It is used to set a trace function for all the threads that are created by threading module. The func function is passed to sys.setTrace for each method. Func, it is a required parameter which is passed to sys.setTrace for each thread. This function is executed before the run method. The return type of this method is class none type. It does not return anything. It sets a trace function for all the threads. Python program to explain the use of setTrace. Passing the trace function and current thread is threading.current thread get name. Creating sample threads. So it's calling this function. Still don't understand. Be more like this standard library threading module. Thread local. The thread goes away, and so too implicitly the effect of systrace is undone in that thread. It's maintaining a thread pool. At the time they are frequently idle until they wake up and process a work item. Then they go back to sleep. To allow for calls to threading.setTrace, threading.setProfile to have some effect, it's necessary for the event to make the corresponding cease calls each time a thread picks up a work item to begin processing. This again is thread local state and shouldn't affect any other thread. There was another method that I could call to threading setTrace. SetTrace function for all threads started from the threading module. The func will be passed to setTrace for each thread before its run method is called. So maybe I'll try this threading setTrace. I think I'll do it here and I'll erase this stuff. This module constructs higher level threading interfaces on top of the lower level thread module. Maybe I need to import. In C Python, due to the global interpreter lock, only one thread can execute Python code at once. Though certain performance-oriented libraries might overcome this limitation, if you want your application to make better use of the computational resource on multi-core machines, I advise to use multiprocessing or concurrent features process pool executor. However, threading is still an appropriate model if you want to run multiple I/O bound tasks simultaneously. This module defines the following functions: number of threads, objects currently alive, return the current threads, exception hooks. Maybe it's because I need to put C's there. Yeah. So yeah, it doesn't. Oh my god. So I need to import this.
Hey there, how's it going everybody? In this video, we're going to be learning how to run code concurrently using the threading module. Now, this has been a highly requested video for some time now, so I'm glad that I finally am getting around to this. Now, I'm also going to be doing a follow-up video showing how to run code in parallel using the multiprocessing module, and we'll also look at when you would want to use one over the other. Now, if you don't know the difference between threading and multiprocessing, then you should have a grasp on the difference between those once we're finished up. Now, I would like to mention that we do have a sponsor for this video, and that is Brilliant.org. So I really want to thank Brilliant for sponsoring this video, and it would be great if you all could check them out using the link in the description section below and support the sponsors. And I'll talk more about their services in just a bit. So with that said, let's go ahead and get started. Okay, so first, why would we want to use threading? So basically, we want to use threading whenever it's going to significantly speed up our program. Now, this speed up comes from running different tasks concurrently. And we'll talk more about concurrency and what that means in just a second. Now, speedups aren't really guaranteed, so it really just depends on what you're doing. So in this video, we're going to start off with a basic example where we learn how to run some simple sleep methods concurrently, but then we'll finish up with a real-world example where we download some high-resolution images from the internet. Now, I want to show that real-world example because, personally, when I watch tutorials that only show how it works with a basic example, then I always feel like it doesn't really, that I don't walk away with any actual useful knowledge. So we'll use the sleep method to get a good idea of how to use threading, and then we'll be sure to go over the more complicated real-world example of downloading images online. So let's go ahead and get started. So I have a starting script open up here, and if you'd like to follow along, then I'll be sure to have a link to this code in the description section below as well. And like I said, we'll start with a very simple example and see how this works, and then build up to more realistic examples. So for the script here, I'm just importing the time method, and then I am starting a counter. This is just so we can measure how long this entire script takes, so you really don't have to pay attention to these. It's not really doing anything on the other function here, and then it comes up here and wait are things that are bound, which is multiprocessing. So here's an example. Let's see how to actually threads. Actually running that. I'm going to sleep for a second, and then it says that our thread. So I will call this T2, and now it's confusing at first. Then definitely stick around because I'm also going to and our 2, and then we can see how to do what we're doing here. So right.
Maybe I need both. Not sure. Oops. Yeah. This. This is the global namespace. Much better. I guess I can erase this stuff.
Right now, we're running a function that doesn't accept any arguments, but let's add a couple real quick so we can see what this looks like. So right now, we're just sleeping for 1 second, but let's add an argument that specifies how long we actually want to sleep. So up here in our do something function, I'm going to pass in an argument, and I'll just call this seconds. And now I will say that we are sleeping for however many seconds, and this needs to now be an f string so that we can pass in the variable like that. And now, instead of sleeping for 1 second, we'll sleep for the number of seconds that we passed in as a variable here. And just so this doesn't say sleeping for 10 seconds or something like that, let's also say that this could be seconds as well. Okay, so now our function is expecting an argument for the number of seconds to sleep. So let's pass in seconds as an argument. And we need to pass that in as a list.
I think I'm gonna print this line number and see what happens. Wait, oh. Okay. Yeah, I don't even know why I need this func name here. I think it was there just because it was func name equals frame.f name. Oops. I already wrote there. Line. Frame object is no attribute line number. Oh, it's F line number. Oops. Now it should work. Yeah, that's the thing though. Huh. I'm thinking about creating a dictionary with all of these values and appending that to a list. But I don't understand how it's working, the execution of the thing. Because I don't see there, I only see the thread and the processes of the Python, but I don't see at any point the functions that I actually want to study from the other script. And I'm not sure if that's because that's how Python works usually. But I feel like it should be showing me, at least on some frames, some of the functions that are on the script that I'm trying to get these frames from. And that's the problem. Maybe I should put this on. It's not gonna make any difference, but I don't understand why this is not being executed as well. It seems to me that it should be. I think I'm gonna close this.
List of arguments. So down here where we create, but depending on the with concurrent dot this a little bit more. So 1 second. Let's grab that. We finished our script in 1 second. Method. And within
Process is a program that's being executed. A process may not be specified by user. It could be a system process spawned by your operating system. You'd be using the library. Firstly, we initialize this library. This allows you to choose function. And it's not what I want. This is more for the system, I feel like. The Windows system, not the Python script. I think I'm gonna take a break and then I'm gonna continue this another time. So yeah, if I don't come back today, later today, I'm probably gonna come back soon. Maybe tomorrow or the other day. So see you.